So today what we shall do, as I told you in the previous lecture, that we shall now calculate this amplitude. We were actually calculating this. We were calculating this, and we know that this is basically equal to, so it is basically equal to this. And what we have done is that we have expanded the S matrix and kept terms up to linear order in the coupling constant lambda. And we have actually considered a lambda 5-fold theory, and we have kept terms up to linear order in lambda. And in the previous discussions, we actually calculated this term explicitly. And I told you that we shall also try to calculate this term. And as you know, this term is a term of order lambda square, and plus higher order terms. We shall not look into these terms for the time being. We shall only now concentrate on this term. So A2, this term is, you can write this term as, so this is basically nothing but Q is, where S2 basically means it is taken up to second order. The S matrix is taken up to second order. And you can write this in the following way. I have a 1 by 2 factorial, then minus I whole square, then we have lambda by 4 factorial whole square. This comes with the lambda 5-fold kind of interaction in your theory, and now we can Q, then we have W time order product of phi to the power of 4 y phi to the power of 4 w. So this is the term that we are after now. So we want to calculate this term. We have already calculated this. This term is trivial, right? There is nothing to calculate. This is basically a delta function, which tells you that the particle just comes from the remote past and it goes away to the remote future without interacting. So the first term that takes into account the effect of interactions is this term, and now we are after this term, and this term you can write it in this way. Okay? And what we shall do is, you know that you can write this state, which is basically the eigenstate of the free Hamiltonian H0. So this is a state in the simple world. So you can write this state in the following way. So we use the relativistic normalization. Previously we were ignoring this factor, but now let us do it by keeping into account all the factors in place. So we were in the previous discussions we were not writing this one, we were just writing get p as a dagger p get 0. But now I'm putting in this factor, and if I put in this factor, so you can basically write this as n p inverse a dagger p get 0. And similarly, you can do it for Q also. Okay? So if you do that, then this expression can be written as this expression, you can write it down as 1 by 2 factorial, 4 factorial, minus I lambda root square, and then from P and Q, we will have factors of NP inverse, NQ inverse. Then we can take the integration outside. This will be d4y, d4w, then this will be bra 0 time order product of A 2. Then we have 5 4 y 5 4 w A dagger T. This is it. So what we have done is we have put in the expressions for ket P and bra Q from here, and these are the factors that come out from ket P and bra Q, and then we have this. So you can see that this is a very long expression, and we need to calculate these terms by once again using the Wick's theorem, because all these are fields in the interaction picture, and therefore these are basically these fields basically evolve by the free part of the Hamiltonian H naught, and therefore, and this is also the hacking of the free part of the Hamiltonian, and therefore you can apply Wick's theorem, and you can work it out. And let us see what is the expression for it. So this is A2. So now let us, for the time being, forget about this factor. Just concentrate on the integral. So we have d4y, d4w, and we want to look at a particular diagram. So you can see that, let me just write it down first and then it will be clear. So what we need to calculate is this thing, AQ, then we have I, Y, there are 4 such phi y's. Then we have 4 such phi w's. Then we have a dagger E. This. And you can understand that evaluating this expression, there are so many terms. So there are 8 operators and 9, 10 operators. And you can do this calculation by applying Wick's theorem. So, and you can see that it will be a very big expression, right? Is this clear? Up to now, is it clear for all of you?
Yes.
And as I mentioned, that there will be 2 kinds of terms. One where you just contract AQ with A dagger P and contract these operators among themselves. So obviously, in the contraction procedure, when you contract these operators, you cannot contract. You have to contract basically phi y with phi w, right? That is how you contract the things. So you have to be careful there. And the other kind of term that can arise is the following. You contract AQ with phi y and A dagger P with phi w and contract the remaining phi's among themselves. This is the other contraction that you can carry out. Okay. So this is one contraction, one possibility that you can get, and the other possibility is to contract this with this, and this with this, and contract the remaining 5 among themselves. So the remaining 5, there are 1, 2, 3, 4, 5, 6 5 among in this expression. So let's see what happens. And now, so you can understand that if you contract in this way, many terms, many possibilities can arise, and to each possibility you can draw a Feynman diagram, right? As we have seen earlier also, when we were considering the first order term, then we saw that what are the possible diagrams that can arise. So here also, to each possible contraction, you can draw a Feynman diagram. Let us today concentrate on a particular Feynman diagram and see how this kind of a diagram can arise. So this is the flow of time. This is how time flows, and this is the incoming particle, and this is the outgoing particle. So this is a Feynman diagram, which is called the Saturn Feynman diagram. The name of this is Saturn. Okay. And let's see how such a Feynman diagram can arise from the contraction of this expression. Okay. Let us just look into this diagram more closely. See, in this diagram, there are external lines. These are the external lines. It's this line. So, in this diagram, there are two external lines. So, these are the two vertices in this diagram, this one and this one. At each vertex, since your interaction is lambda phi 4, you will see that there are 4 lines. So, if you see this vertex, 1, 2, 3, 4 lines. This vertex, 1, 2, 3, 4 lines. So why there are 4 lines? Because it is a lambda phi 4 interaction. There are 4 lines. So it tells you that there are 4 fields coming out from the vertex. This line is called the external incoming line. And this line, if this is your direction of flow of time, then the external incoming line will be always below the vertex. And this line is called the external outgoing line. So this is the outgoing particle. So once again, if your direction of time flow is like this, the external outgoing line will be always above the vertex. And the lines which join the two vertices, the pair of vertices, these lines are called the internal lines or propagators. So you can see that there are quite a few things in this diagram. There are vertices. If every Feynman diagram in any theory will consist of vertices. There will be external lines, external incoming line, external outgoing line, and internal lines or propagators. So this is how this is how a Feynman diagram is built, and this is the general anatomy of a Feynman diagram. In any theory you draw a diagram, this will be the general anatomy. You will have vertices, external lines, and internal lines. And let us now see how this kind of a diagram can arise from a contraction of this expression. Obviously, you have already seen in the previous lecture that if you want to have an external incoming particle, you have to contract A with phi's, right? That we have already seen. So this contraction actually tells you that this is a external incoming line. And also in order to get this part of the diagram, that is, you have an external outgoing line, A dagger P must contract with one of the phi's. And suppose this vertex, I call this vertex as Y and this vertex as W. So you can see that this and this can arise only out from the contraction of this with this and this with this. There are three propagators, so it tells you propagator from Y to V, from Y to W. So it tells you that from out of the remaining 1, 2, 3, 4, 5, 6, 5 operators, there must be 3 contractions each. Okay, there must be 3 contractions
Sir,
between phi Y and phi W. Please.
sir, can you just repeat the part how we can say that a Q and phi contraction leads to the external ingoing and outgoing?
Yes, I will repeat it. You see, you remember when we calculated the first order correction, right? You
Yes, sir.
remember calculation of the calculation to the scattering process up to first order in lambda?
Yes,
There we actually calculated this term, the contraction of this operator with this operator.
yes,
You remember where
yes,
we had put in the mode expansion for phi. So what will you get? You will get AQ phi y. Which term will contribute? Only A dagger,
yes,
because A cannot contribute. And there, if you calculate it, what we found was e to the power of I q dot z, right? From a,
yes,
apart from that np factor, so that is the 1 by square root of 2 pi 2 omega k 2 pi whole cube. That I call as np, and then we have e to the power of I q dot z. So in this case, it will be e to the power of I q dot y. So it tells you that the particle, this actually gives you the outgoing particle. Remember?
okay, yeah.
So
Yes,
you will get the factor of e to the power of I q dot this thing. The plane wave that is coming, that is going outside. And from here you will similarly get the particle is being created. So you can understand how we got that. You remember that calculation? Or should I repeat it once more?
no, sir, it is okay.
It is okay?
Yes, sir.
Good. Just a minute. Okay. So let us carry on. So this and this actually corresponds to the external lines. That is the incoming particle. It corresponds to the incoming particle or the outgoing particle. And now let us see how you can get the internal lines. Internal line you can only get by the contraction of this, like with one of the phi y's, with one of the phi omegas, and there are 3 such contractions possible. So that is how you will get 3 internal lines from Y to W. So one of the possibilities is this, then you contract this with this, and then you contract this with this. So that is how you will get 3 such internal lines. And there are many such possibilities. You can calculate those possibilities, and corresponding to those possibilities, you will get a number. So this diagram you can get from this kind of a contraction, and you can see that there are many ways of doing that contraction, and from that contraction you will get a number. So that number will come outside now. So this number will come outside, and once you calculate the number carefully, you will see that you will get a factor of 6 downstairs. Because there is a number will come out and that will cancel. Oh, so this will be 4 factorial square. This is 4 factorial square. Miss the square here. So the number will cancel this factor and then will give you a factor of 6. Then we will have NP inverse. But let me just write it down in this way. I'm not writing this is equal to this, but this in this term there are many such terms possible. One of the terms which corresponds to this diagram is the expression that I'm writing down. So this full expression, the expression on top, is actually containing this term. So I just replace the equality sign by this sign. This tells you that this term or this diagram is contained in the expansion of this diagram. So that is why I'm just replacing it by this superset kind of notation, or this is basically a subset. This term is one of the terms in this expression. We have already taken into care the factor of 6. We have taken that part out. Therefore, what we shall have now is so you can, this y and w is now irrelevant. Just forget about this. See it like this, because y will be this point and w will be the lower one. So you have this contraction, then you will have the contractions of phi y with phi w, and each of them will give you I delta x y minus w. There are 3 such things. So these 3 propagators corresponds to these 3 lines, and these come out from the contraction of phi y with phi w. And there are 3 such lines. And then the last contraction, this is basically phi w a dagger p. I'm not writing the time ordered product for these terms because there is only one time. So the time ordering is trivial here. Is this clear? Is this part clear?
Yes.
Good. Let me now write it over here. So this term is equal to, you know what these are, you know what these things are. So let us write it down. It's minus I lambda whole square by factor of 6. Then we will have NP inverse, NQ inverse, and from this one and the last contraction, you will once again get the factor of NP and NQ. So this will cancel each other. Then we'll have this d for w, d for y, d for w, e to the power of I q dot y. So that is the outgoing particle, and from here you will get e to the power of minus I p dot w. So these are now taken care of, and you only have the propagators. The Feynman propagators. Okay. Is this clear? So what will happen is these factors will cancel. So you have this particular diagram corresponds to this expression, and we have actually worked it out from scratch. We have actually worked it out by using the Wick's theorem. But you can understand that as you go to higher and higher orders in perturbation theory, the calculations will become more and more difficult, right? It will become more and more difficult and complicated. You can use Fick's theorem, but it will become very complicated because there will be many terms and many contributions. And there will be many kind of diagrams that will arise when you go to higher and higher orders in perturbation theory. But there is a nice way of actually writing down the mathematical expression corresponding to any diagram immediately. For example, this diagram, if I ask you what is the mathematical expression corresponding to this diagram, we have just now calculated it by using Fick's theorem, right? This diagram basically is equal to this expression, and this has been obtained by working from the scratch. We have applied the Fick's theorem and we have obtained this expression. But is there a simpler way of calculating the mathematical expression, this expression, once I give you this diagram? If I give you a diagram, can you write down the mathematical expression corresponding to that diagram? Is there a simpler way of doing that? And the answer to this question is yes. What we have to do is use Feynman rules, which we have already derived. We have actually derived the Feynman rules in our previous lectures. And let us see how we can apply the Feynman rules to write down the expression for this diagram. It is very simple. What we need to do is, we now go to the other side of the board. What we need to do is look at this diagram. So these are the two vertices, and this is the flow of time. So this expression, if you notice, so let me just show you this. This expression, if you notice, this full expression that we have is basically the mathematical expression corresponding to this Feynman diagram written down in position space. So everything here, these are basically the positions, right? So it is written down in position space. So can you write down this expression in position space? We have not integrated anything. Can you write down this expression in position space just by looking at the diagram? So the answer to this question is yes, you can do it, since we have already derived the Feynman rules corresponding to each of these parts. We have the diagram, we have the Feynman rules for the internal lines, for the vertices, everything. And this we have actually derived from the calculation of the correction or from the calculation of only the first order term in the perturbation theory. When we calculated the first order correction to the scattering process, from there actually we derived many Feynman rules in position space. And let us see now how we can apply them. So what I told you there is that corresponding to each vertex, we will have a factor of minus I lambda. Right? We have derived this rule that whenever you see a vertex, you just write down a factor of minus I lambda, and since this is a Feynman rule in position space, you have to integrate over the vertex. Right? So there are two vertices. So corresponding to the two vertices, you get a factor of minus I lambda whole square. So let me write every vertex will have minus I lambda and integration over the vertex. There are two vertices, so we will have minus I lambda whole square, and then there will be integration over the two vertices, over the special integration over the two vertices. So you have applied one of the Feynman rules. Is it okay?
Yes.
Now you have to apply the rules for the external lines. So external lines, I told you, since here we have used a normalization of this form, that is, we have used the fact that ket P We have used this normalization, right? Sorry, A dagger P. We have used this normalization for ket P. And therefore, when we use this normalization, what happened was these factors got cancelled. These factors got cancelled. But so if you use this normalization, then it tells you that corresponding to the external lines, you just, so there are 2 points. What you do is you just apply Q dot. If I call this vertex as Y and this as W, then for this vertex you just apply, since this is the direction of flow of time. So this is the incoming particle, this is the outgoing particle. What you do is apply e to the power iq dot y and then e to the power minus iq dot w. So that is what you do. Okay. So this is the rule that we have already derived. We said that corresponding to the external lines, we will have these factors, these plane wave factors. But there we said that you have to multiply it by np and nq. You will really have a np and nq sitting over here, provided you use the normalization ket p is equal to a dagger p ket 0. If you use this normalization, then there you will have those factors of np and nq coming. But if you use this normalization, then the factors of np and nq will cancel. And then the final rule will be just apply these plane wave factors without the normalization factors. Because for this normalization, the normalization factors np and nq has cancelled each other. Okay? But if you don't use this normalization, if you use this normalization, then we will have factors of np and nq sitting over here. So you should just keep this in mind. So we have got the external lines, and how many internal lines are there? 3 internal lines, and corresponding to each internal line, the rule is just keep every internal line will contribute the factor of I delta F, the propagator, the Feynman propagator. So you have got everything. See, by just applying the Feynman rules, you have written down this expression. But what about this factor? What about this factor? This factor, you just write a factor of D. This is called the symmetry factor. This is called the symmetry factor of a diagram, of a Feynman diagram. So this number, so you have to divide by a number, and that number here is actually 6. So what is the rule to get the symmetry factor? There is a rule, and you can actually derive that rule from combinatorics, but we shall not do it now, but we shall give you the Feynman rule corresponding to the symmetry factor, how to get the symmetry factor. So what is the meaning of this factor? This tells you this is basically a number that arises from the fact that you can contract these things in many ways. So this number basically arises from the number of ways in which you can contract this expression to get this diagram. Okay? So there will be many ways in which you can contract this expression to get this diagram. So this symmetry factor is a number which arises from there. So its derivation is actually arising from here. In this case, the rule is very simple. The rule tells you that if, so let me write down the rule. The rule for the symmetry factor is that if you have a propagator, and you say that the propagator, you have a propagator line, you have an internal line, both ends of which end at the single vertex. So you have something like this. This is a loop. So both the ends of this propagator ends at a single point. So that actually gives you a loop. Then the rule tells you then the symmetry factor for this particular thing will be d is equal to 2. Will be 2. This is the rule. The other rule, which is very convenient to use, is that if you have a pair of propagators like this, internal line, and there are, if you have every pair of vertices directly joined by, say, n propagators, will give you a factor of n factorial. So this is
Sir,
the
I
rule.
couldn't understand the d equals to n factorial thing.
This rule tells you that every pair of propagators joined by n, every pair of vertices joined by n propagators. So in this case, this pair of vertices is joined by how many propagators?
3.
3.
3.
It tells you that every pair of vertices joined by n propagators will give you a symmetry factor of n factorial. So in this case, how many propagators are there for this Saturn diagram? There are 3 propagators, there are 2 vertices, pair of vertices joined by 3 propagators. Therefore, D in this case will be 3 factorial, and that gives you the factor of 6, the symmetry factor. So there are 2 simple rules. Let me just repeat. If you have this a propagator whose 2 ends are joined to a single point, then that, so it gives you a loop basically. So then that particular thing gives you a symmetry factor of 2, and every pair of vertices which are joined by n propagators will give you a symmetry factor of n factorial. So in this case, for the Saturn diagram, it gives you a symmetry factor. Since there are 3 lines, internal lines of propagators joining these 2 vertices, it will give you a factor of 3 factorial, which is 6. So you need to divide this thing by 6.
So, sir, for a bubble, there should be the symmetry factor 2, not 4 factorial.
Which one?
We used the bubble case as 4 factorial. The symmetry
No, no,
factor
no.
was 4.
No. We have not talked about symmetry factors at all in our previous things. See, when we were calculating the first order correction and those things like that, we were actually being sloppy, and I told you that. We were being sloppy about the fact about what will be the correct factor in front of these things, like minus I lambda whole square. What will be the correct factor sitting here? We were actually sloppy about those things. What we were only interested in those calculations were these expressions, the main structure of the Feynman diagram. We were not concerned about the symmetry factor. The symmetry factor is a number which arises, as I told you, due to from the fact that in how many ways can you contract this particular expression, and from there this number, the origin of this number is from there. But when we were doing the calculations of the first order in the perturbation, in the coupling constant, then we were not very accurate about this factor. We were saying that we will give a rule for that factor. We were actually contracting things and trying to get out the numbers. If you put in the numbers, I will suggest you something. You just once again calculate the things up to first order in lambda, and I showed you one diagram there. You remember how did we get this diagram? Remember this, right? Do you remember or not remember this?
Yes, sir.
You remember? Please respond, otherwise it will be difficult. So if you remember this thing, then just a second, I'll tell you. Okay. If you remember this particular diagram, then so what is the structure of this diagram? You see that there are two external lines and there is one vertex and there is one loop, right? So this is the anatomy of this Feynman diagram. And if you remember that this diagram came from the contraction by using the Wick's theorem, and the term in the S matrix expansion from which this diagram resulted actually had a factor of 12. So it resulted from a contraction of A. Can you see this part of the board? So it resulted from a contraction of A with one of the phi's and A dagger with one of the phi's. So, and this was a term up to first order in lambda. So there are only 4 phi's, right? So A contracts with phi, A dagger contracts with one phi. So two phi's are gone, and therefore only 2 remains, and therefore there is only one particular contraction between phi z and phi z. So that gives you a propagator which whose two ends are joined to a single vertex, right? And if you look at that term can arise in how many ways? You have to look at that term. Let me just see once more.
Well,
That term could arise in 3 ways, I think, right? That term arose in 3 ways. Or let me just check once more. I have to go back, or you can also see your notes if you have it. Have
sir,
them in
12 ways, sir. 12 ways.
12 ways. I think
Yeah.
that was in 12 ways. But why is it 12? I'm trying to figure it out. Just give me one second. This contracts with this. Yeah, it will be 12. It will be 12. So let me just write the term. It was basically time-ordered product of vacuum expectation value is a VV A Q phi Z phi Z phi Z phi Z A dagger P. So that completes the time modeling, and like this. So this was the first order term, and here we contracted this with this with this, and the only contraction possible between this and the 2 phi's contracting at the same point. But why are there 12 ways? Because this you can contract in 4 ways, right? 1, 2, 3, 4 ways. Once you contract this in 4 ways, this you can contract in 3 ways, right? And that gives you the factor of 12. Joyashi, are you here? Are you listening? Or do you have
Yes,
left?
sir.
So there are 12 ways of contracting. So this, and this will correspond. So this contraction with this will basically be something like this. So if this is the flow of time, then the particle comes in. You have the vertex. This is something like this. So this particular way of contracting gives you this diagram. And there are 12 such ways, right? And you have a factor of 1 by 4 factorial downstairs. So that is 1 by 24 multiplied by 12. So that gives you a factor of how much in the denominator? 2. Okay? And therefore, and that is what you get, because the symmetry factor for this loop is 2, not 4 factorial. This gives you a factor. If you write down the Feynman expression, Feynman diagram, Feynman rule for this, or the expression, mathematical expression corresponding to this Feynman diagram, you have a 1 by 4 factorial downstairs from the weak expansion, and there are 12 such terms. 12 divided by 4 factorial gives you a factor of 2 in the denominator, and that is precisely the symmetry factor for this diagram. So you please try to apply the Feynman rule for this diagram and see whether you can reproduce the expression that I derived from Wick's theorem. So you can see how you can, so these are basically the Feynman rules. For vertex, you multiply by minus I lambda d4y. There are two vertices, so you will have two such factors multiplied by this integration. So minus I lambda, two integrations d4y and d4w. Two external lines gives you this, and three internal lines gives you the three propagators. And the symmetry factor is, since there are the two pair of vertices are joined by three propagators, each it will give you a factor of 3 factorial. So that gives you a factor of 6. You just put it in the denominator. And this is precisely the mathematical expression for this Saturn diagram, for this diagram. And this actually we have also derived it, excepting the factor in front, excepting the factor, symmetry factor. We have actually derived the full thing by using the mixed theory. So these are all about the Feynman rules in position space. So these are the Feynman rules in position space, and whenever you have a loop, remember that if you try to draw a diagram for this, what will you get? You will get minus I lambda integration over this vertex delta f y minus y corresponding to this thing, and these external lines will give you the factors of e to the power of I minus ip dot y and e to the power of iq dot z. And you can also keep the normalization factors, but you can keep them, and you may also omit them. It depends on the choice of normalization that you take for the states. So let us conclude today's discussion here, and we shall continue from this expression in the next class.
Sir. Sir, from the diagram, from the previous calculation, it is clear which one be plus iq dot y and which one be minus ip dot w to the power. But sir, from the diagram itself, can we conclude what will be the sign of the exponentials?
Yeah, the external line you take, just call this as what? You call this as y, or you call, and this as w. Then this will give you e to the power of iq dot y. But it doesn't matter.
Okay.
It doesn't matter which you call y and which you call w, because y and w's are integrated over. So y and w, when you write this expression, or this expression that we have written, here it doesn't matter whether you call this y and this w, because these are all integrated variables. So these are dummy variables.
Yes, sir.
You can very well call e to the power of iq dot w also, because w and y are integrated over.
Okay, sir.
But so what we have discussed today, the takeaway message of today's lecture is that we have actually derived the Feynman rules in position space in the previous lectures. We have actually applied today the Feynman rules. We have done two things. We have calculated directly using the Weeks expansion, and we have also applied the Feynman rules that we have derived earlier in the earlier discussion to get the same expression that we derived from Weeks expansion. So thank you very much. Let us stop here for today.